All right, so let's take a look at the second example problem for the Centroids and Moments of Inertia lecture. We've got a simplified shape here compared to the parabola that we were looking at before. Here we're given a cross-section, we call like a U cross-section or a channel cross-section. These are relatively common in structural steel shapes. And this section, it shows that there are rounded over corners here, but I'm just going to go ahead and treat these as rectangles as well too, even though they have a fillet. And we could write that down as an assumption as well too. And I believe the call of the question tells you to simply treat these filleted corners as solid. Likewise, there might be a fillet in these corners here. We're just ignoring all of that. We could sharpen the pencil and look at it in a little bit more detail, but usually for these type of calcs, it's only going to change the answer a couple percent, so we usually just ignore that. But either way, we've got this U or this channel shape. We're given the dimensions and we're told to find the area of the shape, the centroid location, so the location of the overall centroid of the entire shape. That's where the X sub C and the Y sub C axes come through. The moment of inertia about the X sub C axis, that's centroidal X-axis, and the centroidal Y-axis, that's parts C and D. We're asked to find the polar moment of inertia about that centroid. That's really easy. That's just going to be equal to I XC plus I YC. And then the radius of gyration about that centroidal axis as well too. I'm not even going to go through these because there's not really much of a calculation. It's simply equal to I XC plus I YC. And the radius of gyration is simply going to be equal to the radical of I XC divided by A. So those are often asked because they're important cross-sectional properties, but the calculation themselves are super easy. So we're going to focus on A, B, C, and D because that's where the actual work gets done. And then reporting J and R is really just kind of an afterthought at the end because it involves one very simple calculation for each. Okay, but looking at area, looking at centroid and moment of inertia gets to be a little bit trickier, but the good thing about a problem like this is that if we can break down our shape into simple geometric shapes like rectangles, triangles, maybe circles as well too, then we can easily calculate each of those required values kind of in tabular form. There's an easy way to kind of organize our work. So the way that we do that is by breaking up the shape into kind of bite-sized components. Components that we know really easily where the centroid is, really easily what the moment of inertia about their own local axis is. And that's kind of what I've done starting with the solution over here. So I'm not even starting to calculate the area or the centroid or anything else. I'm just going to start mapping everything out. And how detailed this image gets, or this figure gets, is going to be, that's going to help you with the rest of the calculation. So the more detail, the more space you give yourself, the easier it's going to be later on. So what I've done is I've looked at this channel and I've said, I see 3 different rectangles. That's a fine way to go about it. I just made the bottom rectangle the full width of this shape, and then on top of it I put 2 other little rectangles. Now there's nothing wrong if I would have instead shown the side rectangles going all the way to the bottom and then the bottom rectangle butting up against these side pieces. If I had this joint instead of that joint, it won't change the answer, it'll change the math, but there's nothing wrong with that. I would also point out that some people might look at this shape and they would say, I don't see 3 rectangles, I see 1 big rectangle and then 1 negative rectangle. And that is absolutely okay to do. Now the math gets to be a little bit trickier because when we're adding up areas, if we're adding up moments of inertia and things like that, you need to be careful about the relative sign, but there's nothing mathematically wrong with saying I have a large positive area and I'm subtracting out the effects of this negative area. Totally works, not a problem. Your book has some really good examples of that as well too. But what I've done is I've simply broken it up into three, what I'll call positive areas, and then you could check your work later on using a positive area and a negative area if you want to. So what I want to do for this shape is I want to identify all of the relevant geometry for each of these, now what I'll call three kind of sub shapes. So looking at this here, I'm going to go ahead and call this left rectangle, the top one, shape 1. I'll call this one shape 2. And then the large rectangle in the bottom, I'll call shape number 3. And so for each of them, I need to identify the location of the local centroid. So for each of these shapes, they have their own little mini centroid. And because they're all rectangles, that's really easy to find. It's just at the half height and half width for each of them. And so this will have a little centroid down here. And then shape 2 over here on the right will have a centroid as well. And if we're talking about like the X and the Y as the bottom and the left axes, that's going to help us kind of identify coordinates for each of these. So a little bit more kind of data on this is going to be helpful. And so let's just identify for these the coordinates of each of the centroids. So here, the distance from the x-axis up to the centroid of shape 1, I will call that y tilde 1. The tilde simply means that we're looking at the centroid location for a subshape, not the overall shape. And likewise, shape 3 here is going to have y tilde 3. And shape 2 is going to have y tilde 2. Now, these are going to be relatively easy to calculate because I know that the centroid of this is half the height of the rectangle, and then I simply add on the thickness of the bottom rectangle. And so it's going to be relatively easy to calculate these. I just want to have them shown schematically. And I'll do the same thing for the x's as well too. So here's x tilde 1. This distance here will be x tilde 3. And then this distance way over here is going to be x tilde 2. Okay, so I have each of the locations of the centroid shown. I might as well show the distance for x sub c and for y sub c. Those are the coordinates, or the location of the centroid of the overall shape. So I have not only the centroid of each individual subshape, but the overall centroid shown as well too. And that's going to come in handy a little bit later on. I'll add some more values to this later on, but this is enough to get us started in terms of solving for A and for B. So if we're looking at the area, area is simply equal to the summation of each of the individual areas for shapes 1, 2, and 3. So I just say area equals the summation of A sub I being like 1, 2, and 3. And because for these shapes, they're all rectangles, I could also simplify that down to the summation of B sub I times D sub I. In other words, the width B times the depth D. And so that might be a helpful thing to kind of get started with here is I'm going to have each of my shapes, so 1, 2, and 3, and I'm going to tabulate the width in inches and the depth D also in inches, and then I'll tabulate the area, which is in inches squared for each of them. Now, once I've done that, I can simply add up each of the values here to get the total area of the shape. So it's just some bookkeeping. That's the easiest place to make a small mistake here. We're just simply bookkeeping. And so for shape number 1, the width is given as 10 millimeters. We can assume that this is symmetric about the vertical axis. So the width is 10, and I'm sorry, I was drawing things in inches here. We're actually just talking about millimeters. So millimeters here, millimeters squared. And so the width is 10 millimeters. The depth, this height right here, is given to me in the given statement is 50 millimeters. So I get 500 millimeters squared. For shape 2, it's the same exact thing. 10 millimeters wide, 50 millimeters tall, 500 millimeters. And then finally, this bottom shape, shape 3, has a width B of 300, which is 150 plus 150, and then times a thickness, which is given as 10 millimeters. So I get an area of 3,000 square millimeters. So this is nothing new. I think what might be new is that we're being really rigorous about keeping everything in a table. But then finally down here, I simply add everything together, and I get the area is 4,000 millimeters squared. So I say area equals 4,000 millimeters squared. Okay, so far so good. We've dealt with part A. And now we need to start calculating the location of the centroids, which is part B. And so the formula for part B is simply that x sub c equals a summation of x bar I times ai divided by the total area. And y sub c equals a summation of y tilde I ai divided by a total. What this is saying is that for each shape, I multiply the distance to the local centroid of that individual shape times the area of that shape, and then I divide by the total area of the entire cross-section, all 3 shapes added together. And I do the same thing for the y's as well too. So what's going to make sense here is if I were to tabulate the x tilde values, if I were to calculate the x tilde times a values as well too, that's going to be the way to figure it out. Because I can simply sum up everything in this column right here, divide by the total area, and that's going to give me x sub c. Now, the calculation will give you the correct answer. It's just a little bit of work. It's all simply algebra, not a big deal. But for a shape like this, where the location, the distance to the centroid here, xc, for this horizontal distance, if I have a shape that's symmetric about that vertical axis, then I don't need to do the calculation. So here, this is a symmetric shape about the vertical axis, and so I can simply write down, due to symmetry, x sub c simply equals 150 millimeters. And so 150 millimeters, and I'll just put a star right there, and down below I will say due to symmetry about y sub c axis. I would get the exact same result if I calculated x tilde, multiplied it times the area for each of these 3 shapes, added up this column, divided by that column. I would get 150 millimeters. But if you want, you can just simply say, due to symmetry about this vertical axis, it's simply equal to half the width. That's totally fine as long as you make a note. So what I'm going to do instead is I'm simply going to do the next part for y sub c. I'm going to calculate y tilde and then y tilde times a for each of these. And so let's go ahead and look at shape number 1. Shape number 1 is a 50 millimeter tall rectangle, and so its local centroid is 25 millimeters above the bottom of it, which is in turn 10 millimeters above the x-axis. So 10 plus 25, the distance from the x-axis up to that centroid, that y tilde 1 value, is simply going to be 35 millimeters. And just putting units on these. Same thing will be true for shape number 2. 25 millimeters above the bottom of that rectangle, plus it's sitting on top of a 10 millimeter tall rectangle, I get 35 millimeters as well. And then finally, the vertical distance to the centroid for the big bottom rectangle number 3 is just half of the height of that 10 millimeter tall. And so it's going to be simply 5 millimeters. And all that I have to do at this point is multiply the area times the distance to the centroid in the y direction to get the y tilde times a values, which is simply the numerator of this equation. So when I do that, I get 17,500, 17,500, and 15,000. And when I sum those up, I get 50,000 millimeters cubed. So all that I have to do is plug in this number, which is 50,000 millimeters cubed, divided by the total area, which is 4,000 millimeters squared, and I get a value of 12.5 millimeters. Now, here I can check that that's reasonable. It's between 0 and 60 millimeters, that makes sense. But most of my area is down here in the bottom due to this really large 10 millimeter thick rectangle in the bottom. And so the centroid should be below half the height, which would be below 30 millimeters, and it is. It's at 12.5, which is, closer to this bottom rectangle because that's where most of the area is. So it passes a reasonableness test. My units work out in millimeters, and so far so good. I've got the location of that centroid in addition to the area. So these first calculations, lend themselves to be put in tabular format. And again, if we didn't have symmetry about this vertical axis, I would simply have another 2 columns for x tilde and x tilde times a. But because of symmetry, I don't need to worry about it. Okay, so at this point, we're doing pretty good. Everything's organized. We've got a nice figure to go around with everything else. Now we need to worry about the moment of inertia, and that gets to be a little bit trickier. So I'm going to make a little bit of room here and put the equation up top for the moment of inertia. So we'll go ahead and do the moment of inertia about the x-axis first. And the moment of inertia about that, x sub c axis, which is this axis right here, I'm not getting the moment of inertia about this bottom x-axis. I'm getting the moment of inertia about the centroidal axis that's parallel to the x. And that's going to be equal to the summation of I naught, or Ix naught, which we'll talk about in a second, plus a times dy squared. So what this is telling me is that for each of these 3 individual shapes, I take the moment of inertia of each shape about their own local x-axis, or their own x-axis that passes through their centroid. There's a moment of inertia about just that point, plus the area of that shape times its perpendicular distance from our axis of interest. And let's just go ahead and draw or show what that distance is. So Ix naught we're going to get out of a table in the back of your book or on the formula sheet. That's not a big deal. This is simply going to be 1/12 base times depth cubed. And we already have b and d here, so that's not a big deal. The area, this is just simply the area of each individual shape. We have that in the table here already. dy is the perpendicular distance from the local centroid to our axis of interest. So if I were to draw that distance for shape 3, here is the local centroid, and the perpendicular distance from our axis of interest looks like this. So that's this distance. This is dy sub 3. And I drew these centroids as kind of in line with the overall centroid, but they're not. I'm going to take a little bit of artistic liberty here. This distance right here will be dy sub 2. And then same thing over here. There is some perpendicular distance between the centroid of shape 1 and the x sub c axis. So those are relatively easy to calculate because they are simply equal to y tilde I minus y sub c. The y component of the centroid here minus this distance y sub c. So it's like y tilde 1 minus y sub c. So we can calculate those pretty easily. So let's go ahead and start tabulating those because that's going to be an important value. I'll get the blue. Actually, I'll change the color here. So here for dy, it's still going to be in millimeters. For y1, I have a y tilde of 35, and then minus the distance of the centroid. Okay, and so that's going to be 35 minus 12.5. It'll be 22.5. And I'll have the same thing for shape number 2. The distance to the centroid of shape 3 is 5 millimeters. Minus 12.5 is minus 7.5 millimeters. Now the good thing is that because this term ends up being squared, the dy term ends up being squared, the negative symbol doesn't really matter. You can include it, but it's really the magnitude of dy that we really care about. Okay, so then the other terms that I need to tabulate here would be a times dy squared, and that's going to be in units of millimeters to the 4th. And so all I'm doing is taking this area times this distance squared, and I get some pretty big values. I get 253,125 for both shapes 1 and for shapes 2. And I get 168,750 millimeters to the 4th for shape number 3. And we will need to sum these up. That's going to be the second term in our moment of inertia equation. So I will need to sum those up. And I do get a value of 167,000. No, that number doesn't seem right. 253. I'll have to double check that value in just one second. So that value would be around 700,000 something. 253,125 times 2 plus 168,750 would be 675,000. Okay, now I need to also tabulate Ix naught, which is also going to be in units of millimeters to the 4th. And this is simply telling us what is the moment of inertia of this shape 1 about its own local centroid. And that's simply based off an equation out of the back of your book, because the overall moment of inertia is due to not only this shape's moment of inertia about its local axis, but also that AD squared term is called the parallel axis theorem. But we still need to include this other part, what we call Ix naught. And for using 1/12 base times depth cubed, I get values of 104,167 for both shape 1 and for shape 2. And then for the bottom shape, for shape 3, I get 25,000. And if I sum up those values, I get 233,334. And then all I have to do to get the overall moment of inertia, both due to these shapes' moments of inertia about their own axis, plus their area times the distance to the centroid. So if I add those together, IXC equals 908,334 millimeters to the fourth. That's simply this number plus this number. And so if I were to plug that in over here, equals 933,334 millimeters to the fourth. The same exact process is followed to get the moment of inertia about the y sub c axis as well. So whereas these terms right here are for IXC, the next three terms here need to be for IYC. And that's going to be dx, that's going to be a times dx squared, and that's going to be I y naught. Millimeters, millimeters to the fourth, and millimeters to the fourth. Now, what we need to do is we need to show on our plot up here what that dx value looks like, and that's, again, defined the same way. It's going to be the perpendicular distance from the local centroid to the axis of interest. And I'm just going to change these values to xi minus xc. And I'm just going to change these values here. IYC equals IY naught plus a times dx squared. So if I were to plot them out over here, for shape number one, the distance dx1 is from this local centroid to this axis of interest. dx3 is simply equal to 0. And that's because the local centroid of this bottom shape 3 is in line with the overall vertical axis that we're taking the moments of inertia about. So there's no perpendicular distance between them, so that's just going to be equal 0. So that's a super easy one. It's nice if we can get zeros in these tables. And then finally, this distance here is dx3. Oh, sorry, dx2. That's shape 2 on the far right-hand side. Okay, so if I were to calculate those values, it's simply equal to the x coordinate of this local centroid, which is going to be 5 millimeters from the left side of the beam to here, and then minus 150 millimeters. So it's going to be negative 145 millimeters. From here, the x component of the centroid of shape number 2 is 295 millimeters from the far left side, minus 150 millimeters will be positive 145. And now all I have to do is just take this value, square it, and multiply it times the area itself. So I get some big values. They're all positive because this term ends up getting squared. I get 105,125,00. So over 1 million for these. So 10,512,500. And then 0 down here. So the summation is going to be 210, 2500. And an extra 0. Okay, there we go. Summing up the a dx squared terms here, and then I y naught, this is where we need to make another change up here. Instead of the b times d cubed, it's going to be d times b cubed. That's simply because we're looking at a different axis. Instead of the x-axis, we're now looking at the y-axis. So we're simply flipping the width and the depth terms when we're calculating the moment of inertia about the local centroid. So using this equation, 1/12 the depth times the width cubed, I get 4,167. and I get 4,167. You notice that almost all of the values for shapes 1 and shape 2 are nearly identical because of the symmetry and because of the same size. And then for shape 3, this has a really big width, and that's the term that's being cubed, so we're going to get a big number. The depth is a little bit smaller, and we get 2, 2, 5, and then 1, 2, 3, 4, 5 zeros. And if I sum those up, I get 2, 2, 5, 0, 8, 3, 3, 3. And I kind of ran out of room, so I apologize for that. And all we need to do to calculate the total moment of inertia, which is due to both the parallel axis term and the moments of inertia about the local centroids, if I add up these two values together, I get that IYC equals 4, 3, 5, and then 5 threes, millimeters to the fourth. I could plug that in over here. I could put in scientific notation as well too. 4.35 times 10 to the 7th millimeters to the fourth. I could easily change that into meters to the fourth if I wanted to, but everything's given in millimeters, so unless the question tells you otherwise, it'd be fine to leave them in millimeters to the fourth. But that's how you go about it. And then, like we said, the trivial additional calculations would be to add these two together. That would give us the polar moment of inertia, which is used for torsion. And then to get the radius of gyration, I simply take the moment of inertia about the x sub c axis divided by the cross-sectional area, then take the radical of that. Like I said, these are not very calculation intensive steps, and so I'm just going to write down the formula, and you can review the calculation from the examples in the book. So this gets to be complex in terms of bookkeeping. Make sure you give yourself plenty of room for your figure up here. Make sure you give yourself plenty of room for the tables. You might want to even split these into two. But I want to see both of these for this type of a problem. You need to organize kind of your work, and questions like, are you making the bottom rectangle go all the way out to the sides, or are you making the side rectangles go all the way top to bottom? Things like that are easy to mix up if you don't have a very good diagram, and that's going to make your calculations down below trickier. It's just like with the free body diagram and equilibrium equations. They need to work together, and the more detailed they are, the fewer mistakes you're most likely going to make. So the next steps with something like this would be in EAS 212, actually using these values that we get to calculate stresses, deflections, things like that. But you're going to have to wait until next term until we start actually applying these concepts.